to present our presentation for group 1, set about sets. Well, when we are looking about sets, is defined as a collection of objects known as members of elements. A set has to have some members inside it so that you can show let's say a set A has got 1, 2, 3, and set B has got 5, 6, 7. Those numbers I put in the set, they are members of that set. Is notation, typically we denote sets with the uppercase, while
Zivumba Alec, can you
set
just wait a little bit? Zivumba Alec, is it Zivumba Molek? May you please turn off your camera? May you please turn off your camera?
Should I continue?
Yes, you can continue. I'm sure he hit me.
Okay. This that I was reading. It's a notation. Typically, we denote sets with uppercase letters, while elements are indicated by lowercase letters. The following notation is used to show set members, means that X a member of the set A. There is a X down there, which shows that it is the member of set A. This sentence I was trying to read means that I mean when you are drawing a set, indicate your set with the capital letter A and the other set with capital letter B. What is in the set, you must indicate using the lowercase. Then there is a sign that shows E, which is between X and the A. It means that X is the member of A. The other sign, which is between X, down there, X, and that sign which is cancelled, it means that X is not the member of A. Can I go to next? I don't know how to do it. Sorry, sir. Yeah, thank you. Common set of now is equals to members. There is 0, 1, 2, 3, and so. The set of natural numbers. Then Z has the set of integers, which is -2, -1, 0, 1, 2, and so. Q holds the sets of rational numbers, whether it's P or Q. P is the element of Z. Q is the element of Z. And Q is not the element.
There is a hand by Colin. Is it a contribution or you want to ask something?
Sorry, say I can't see the next slide. I don't know, maybe it's only me or others can see.
Okay, let's just hear from others. Are you seeing the slide or just seeing the previous slide or the first slide?
We are seeing the second slide.
The current slide?
Yes.
It's in common set of numbers.
Okay, it's fine. So I think Collins, your network there, maybe you can just rejoin. You can proceed. Antoinette, you can proceed.
Okay. What I was trying to say above, the meaning each set should be represented by the capital letters. What is inside the set should be presented by the small capital letters. Next slide. Some special sets, the the null set or empty set, this is a set with no elements, often symbolized by that symbol which looks like a zero cancelled, which is cancelled, or those brackets which are empty inside, that shows this is the empty set or a null set. Then the universal set, this is the set of all elements currently under consideration and is often symbolized by that U or the other sign is over there. As you can see it. Next slide. Can you go to next slide? Okay.
Why should I have to go to the next slide? I think this is the current slide that you have to explain. The membership relationships.
I can't. Pardon, say.
I'm saying this is the current slide.
Member, pardon. Okay. Membership relationships, definition subnet. A is a subnet of B. Our set, there are two sets over there. There is a big set and a small set. A big set is presented by B, where its elements is C, D, E. A has got A and B, and those elements are written in small letters, while the sets are presented by caps lock. Right. Here the sign A and B over there. There's a sign between the A and B, which shows that A is the subset of B. A is inside the B set. If all of the members of A are also members of B, then we say that A is the subset of B. Subset is written similarly to the notation for less than or equal to, and in terms of signs in terms of set, it signifies included in or equal to.
But I don't know to the group members. Is it the image that we have there of the set A and B? Is it the correct diagram that we must have there? Where subset and a proper subset, there is a subset and there's a proper subset. Hello.
I think A is like a subset of B, and A has the elements A and B, and then B C, D, and E.
Okay, what about this symbol which is being used for a subset?
This,
What about for the symbol being used?
The symbol X is an element of A.
No, this symbol for a subset. This symbol. You are saying if all of the you, you are just saying if all of the members of A are also members of B, then we say that A is a subset of B. We are saying if all members of A are also what? Members of B. So in other words, A and B are equal sets on that symbol. It's written similar to the notation for less than or equal to, and in terms of sets, it signifies included in or equal to. Then there is a proper subset which will be looking like that, a proper subset, where we have got the elements like in A, but also you have extra elements which will be in B. So the A will be actually the set which will be having the elements which will be common in B and what and A, but we have extra elements which are in B. I don't know if you are getting me. Well, I'm sure on this one is the one which actually tells us about the proper subset, that shape, that diagram. There is a proper subset. We said the statement A is a proper subset of B is if every member of A is also a member of B, we may state that A is a proper subset of B, but there must be also be at least one element C that is such that I think the statement here is it's not well written. A is a proper subset of B, but there must be also be at least one element C that is such that it is an element of what? Of B, but it's not an element of A. I'm sure it's the statement that was supposed to be there. I think it was cut short there. I think you can just continue doing it. There's a end. Sorry, there's a end. I don't know. Let me just check. I was out of there's end by Tando. The Tando Luengos Grace. You can contribute or you can ask a question.
Oh, I was trying to explain the fact that A subset of B means that the elements in A are there
Yes.
in the set B. All the elements that are found in A are there in the set B.
Okay. Which is also correct, but I was just saying the symbol that we are using there.
Oh, all right. That one that says A subset of B. There's supposed to be a line underneath, I think.
There wasn't supposed to be a line underneath it, because it's just a proper subset. I'm saying the set which is there and the I'm saying the set that you've put there and the symbol that you've put there. So maybe we're supposed just to put the proper subset there for that shape.
Oh,
To explain it where so that we can see the difference of a proper subset and a subset. There's a proper subset and a subset. For a proper subset, we have some, maybe you can, if we say A is a proper subset of B, we are just saying there are some elements which are in common in A and B, but there are extra elements which are in B, which are not in what? In A. So that shape is actually a demonstration of a proper subset rather than a subset. Because a subset for that symbol, for a subset, it will be actually almost like A is equal to B. It's like they are equal sets. So I think, Andrew, you can continue. if we do not have other contributions.
Okay, thank you, sir. Definition for proper subset. The statement A is a proper subset of B. If every member, sorry, the slide has changed. If every member of A is also a member of B, we may state that A is a proper subset of B, but they must also be C. But subset is written similarly to the word less than, and in terms of state, it implies included in, but not equal to. A equals A, B, and B is equals to A, B, C, D, and E. Finite and infinite set. If a set S has exactly M distinct elements, where M stands for a non-negative integer, it is said to be finite. In this instance, we write S equals M, or N brackets S equals M, where S coordinate cardinality equalifies a set is not infinite. It is said to be infinite. Example, the English alphabet's collection of letters S is there is no end to the set of positive integers 1, 2, 3, etc.
I think in simple terms, when you are talking of finite sets and infinite sets, you are just like a finite set set which have got a countable elements in it, something that we can count, like the example that you gave of an alphabet collection, an English alphabet, which is a collection of letters, and we can find the cardinality of it, or the modulus of S, or the number of elements in S, which is equal to 26. But if it is a set of positive integers, it stretches maybe from negative infinity to positive infinity. So we cannot, it's not possible to know the exact cardinality or the number of elements in such a set. So that's the difference between an infinite set and a finite set. You can continue.
Okay, sir. I can't see the next slide. Okay. Equal sets. Only when both sets contain the same elements and they considered equal, A and B are equal if and only. If and only X in brackets XA X is times A times B. If A and B they are set on top, the orange one and the light green. A has got the elements A, B, C, D, E. B has got the elements C, D, E, A, B. If A and B are equal sets, we write A equals B. Example, since both sets 1, 2, 3, 1, 2, 5 and 2, 5, 1 share the same components, they are equal. The listing of sets components is any particular sequences is not required, like what's happening above there. A has got A, B, C, D in A, B, C, D in a correct sequence, but B has started with the C, D, E, A, B, and they are considered as equal, no matter the list here, the elements are written not in sequence or not in sequence. The fact that a set elements are stated more than once is also irrelevant. So the set 1, 2, 2, 2, 2, 5, 5, 5, 5, and 1, 2, 5 are equivalent because they contain the same items.
Yeah, exactly. So Tim, on the issue of equal sets, if you look at the equal sets and the subsets there, I think you might see that if you've got equal sets, somehow is the other set is a subset of what? Of the other, because they are what? They are equal what? They are equal sets. So what I just want to stress here is the issue of equal sets. You can just go and have a read on them. So not on equal sets, but on the subsets. You can just go and have a reading on them. Whenever you have a proper subset is just a special type of a subset. So in general, we've got one what we call a subset. And whenever adjusting something is a subset of a set, it means that if it contains some elements which are also common in the other set. So when you are now saying a proper subset, it's now a special type of a what? Of a subset, which means now that's where we are saying if you are saying A is a proper subset of B, it means that there are some elements which are in B which are not in A, but all the elements in A are also in what? Are also in B, just like that. So it's just a matter of mastering the symbols there. That's what I want actually to add here. So I think you can continue.
Okay, sir. Venn diagrams. Venn diagrams, which bear the name of the English mathematician John Venn, who popularized 81, can be used to graphically depict sets, like the Venn diagram which is on top of the rectangles are used in Venn diagram to symbolize the universal set U, which contains all the objects being considered. Sets are represented inside of this rectangle using circles or other geometric shapes. Points may occasionally be used to indicate a set's specific elements. Venn diagrams are frequently used to show the connections between sets. Power set. Given a set S, the power set of S is the set of all subsets of the set S. The power set of S is denoted by P brackets S. E.g., the power set of the set brackets A, B, C is the set of all subsets of C. that in bracket A B C is equal to A B A B A C B A B B B C C A C B C C.
Okay, my question to you, the presenter and your group is that what is the formula for getting all the subsets that we must have in our power set? What is the formula for getting the total number of all the subsets that we can get from our set? So it's like want to know the sets that we have in our power set, the total number, so that you can verify if you've actually come up with the correct answer or the total number, the correct total number of subsets that you can have. Maybe if you can answer it, you can answer. Also, the group must be there to support you.
I think power set is equals to 2 to the power of n, which is the number of elements in a set yacho. Like for instance, if there are 8 elements, you say 2 to the power of 8, and then you punch that and you get the answer.
Exactly.
And then
that's correct.
I've got a question. Say
You can ask.
per equal sets, if I have the cardinality, let's say the numbers are repeating, like that example, A had 252 and then B had 25252 the cardinality of that set, is it different or is the same? Because my numbers are repeat at the other side and the other side is just 3 numbers.
We do not take repeating groups, just count those numbers. Like one number, if you've got 3 2s, just count it as 1. Do not consider of the repeating groups. Also, here on the issue of power set, you have to know that guys, if you are given the set S with ABC, you have to know that that set ABC is also going to be the power of is also going to be part of the power set. Also, an empty set is also going to be the set of a power set. So ABC, we must see ABC. Also, we must see the empty set as part of it. So I don't know your answer here if it is correct. Your answer that you gave us here. Is that correct answer? The power set of ABC. Is that a correct answer?
No, it's not correct, because it should start with an empty set first, and then the list of elements, and then A, and then B, and then C, and then A, B, A, C, and then A. Does it repeat?
So also it's not a must to start with an empty set. You can even put it at the middle or at the end, but it must be part of that. It must be part of that. So I don't know. Because I think the class needs to know the correct answer there. Class needs to know the correct answer. What's the correct answer there?
I think the correct answer is 2 to the power of n.
And that one will give you the total number of the sets that you are going to get.
Yes. So
But
there should be. I don't
so,
know if this is.
So it should be 2 to the power 3, which is going to give us what? Which is going to give us 8. So you must have 8 subsets there.
Yes.
We must have a total number of
Including
8. So 8 is not the answer that we are looking for here, but we are looking for total number of 8 of the subsets that we can make here, which means the first one is the ABC itself, right? And then the second one is the empty set. Then we are left with what? With the 6. Then we are left with the 6 subsets. So how do we get such subsets? Let me just see if I can get my highlighter here. I'll be writing. Let me try to. Okay. Let me pick a green. So you are saying A, B, C. This one is the subset 1. Also the empty set. Sorry, I'm just writing using. The empty set is also the second one, and then the next one is the A itself. A is a subset of this one. The B itself is also a subset of that one. C itself is also a subset of what? Of that one. And then now you can pair AB. You can pair maybe AB, right? And then after that, maybe you can pair what? AC. Maybe you can pair AC. What else? You can pair BC. Can pay BC. So how many sets do we have? This one, 1, 2, 3, 4, 5, 6, 7, 8. And they're enough. So you don't need to repeat this AA. This one, you just write this A on. Then there is AB. This one's just an A. This one's just AB. This is just maybe AC, which is right. But BA is just the same as what? As AB, this one. BB is just this, you have to write B only. BC is just the same as what? As CB. We are talking of sets. So this is a set with BC is equal to a set with the CB. This set CC is just the set as good as a set with this only C. Like what we have said, we do not count these repeating groups. So this one's just a B, this one's just a C, this one CB is just the same as BC, CA is just the same as what? As AC. So this was supposed to be your answer, which is here. I hope you are together. I hope I am not alone here. Is it unspeakable or lost?
unspeakable.
Yeah,
Okay.
it's unspeakable.
Tativunze because on what you are so quiet. Okay, it's fine. You can continue.
Okay.
Let's move. Let's move. You are very slow.
But
I gave you I gave you
Cartesian
1 hour. I gave you 1 hour 20 minutes. Now you are in 52 minutes. Let's move. Let's move.
Cartesian products. It's my network says sorry. The Cartesian products. Let A and B be sets. The Cartesian product of A and B denoted by A times B is the set of all ordered pairs A, B, where A is the element of A and B is the element of B. Hence, A times B is equals to A, B. A is the element of a capital letter A. B is the element of capital letter B. Example, what is the Cartesian product of A is equals 1, 2, and B is equals to A, B, C. Then the solution, the Cartesian product of A times B is A times B is equals to bracket 1A, 1B, 1C, 2A, 2B, 2C. Note that the Cartesian product A times B and B times A are not equal unless A, the set is empty, or B, the set is empty. So that A times B is equals to the set is empty, or A is equals to B. Cartesian products. The Cartesian product of the set A1, A2, and so on to AN, denoted by A1 times A2, and it goes on to AN, is the set of ordered N tuples A1, A2 to AN, where A belongs to capital letter A1 for I is equals to 1, 2, so on to N. In other words, A, capital letter A1 times A2 times so on to AN is equals to A1, A2, so on to AN. A is the element of A1, for I is equals to 1, 2, and so on. Then in Cartesian products, examples. Example, what is the Cartesian product A times B times C, where A, elements of A is 0 and 1. The elements of B is 1, 2, and the C 0, 1, 2. Solution, the Cartesian product A times B times C consists of all ordered triples A, B, C, where A is the element of A, B is the element of B, and C is element of C. Hence, A, B, C is equals, their element is 0, 1, 0, 0, 1, 1, 0, 1, 2, 0, 2, 0, 0, 2, 1, 0, 2, 2, 1, 1, 0, 1, 1, 1, 1, 1, 2, 1, 2, 0, 1, 2, 1, 1, 2, 2. Note that when A, B, and C are sets, A, B A times B is in bracket times C is not the same as A, B, C, which is not in the own brackets.
Let me just add a few here, Tim. When I'm doing cross product, a Cartesian. So when you're doing a Cartesian product, it's not like you are doing a multiplication like what you do in algebra. It's a little bit different. So there's a cross product of just 2 sets, and then there's a cross product of more than 2 sets. So I think that's what you are seeing here. That's what you are seeing here. So this one was just a cross product of just 2 sets, where you have to do a cross product of set A and B. So what you'll be just doing, you'll be just giving us the pairs of A and B, while where the A here belongs to this set A, and then this B belongs to set what? To set B. So if you are given the set A with 1, 2, and set B with A, B, C, if you're asked to give a cross product or a cross product of A, B, what you have to do is to match everything here, maybe with everything here, but you'll be not multiplying. So for this one, it was going to be this one and A. That's why I've got 1A. Then 1 and B, that's why you've got this. And then 1 and C, that's why you have got this. And then you go for 2 and A, that's why you have this. Then you go for 2 and B, and then you do the same. You go for 2 and C. Then on a Cartesian product with 3 sets now, what you have to do is very simple, but you need to keep track of it so that you cannot easily lost. Like here, we start with this 0, and then you go to this one, and then you go to this one. So it's 0, 1, 0. And after that, you go again to 0, you go to 1, and then you go to this one. That's why you've got 0, 1, 1. You go to this 0, you go to this 1, you go to this 2. That's why I've got this 0, 1, 2. Then after that, we have actually made this one with everything here. So you have to shift from this one to this one. So it will be again 0, but now you are going for a 2 and then 0. That's why I've got this 0, 2, 0. Then it's 0, 2, then 1. That's why I've got this 0, 2, 1. Then it's 0 again with this 2, with this 2. That's why I've got the 0, 2, 2. So after that, we've actually matched this 0 with this one with everything here. Also 0 with this 2 with everything here. So you move to this 1. Match it with the 1 and everything here. Also match it with the 2 with everything here. So you just go for 1, 1, 0. That's why I've got this 1, 1, 0. After that, you go for a 1, 1, 1. That's why I've got this. Then you go for a 1, 1, 2. That's why you have this. And then you go for a 1, 1, 1, 1, 1, 2, just like that. And then after that, if you finish that, what you have to do now is to go for this 2. So you have to make this 1 with this 2 with everything here. So that's why you've got a 1, 2, 0 here, then a 1, 2, 1, and then a 1, 2, 2 here. So that's how you do a cross product of what? Of more than 2 sets. Also take note of this. A cross B in brackets, then cross C is not the same as A cross B cross C, as you will be actually required to do A cross B and then you do the cross C. I don't know if there are questions. If there are no questions, I think you can continue now. Andrew,
Okay, so
okay.
set operations, there are numerous ways to sets. For instance, we can create sets of computer science majors, students who are joint majors in mathematics and computer science, and all students who sorry, my network is very bad. Mathematics majors and the whole set of computer science majors. Next slide, say, yeah, thank you. A set union. A union B is the set of elements that are in A or B or both. The elements X belongs to the union of the set A and B if and only if A belongs to A or X belongs to B. i.e. A union B is equals A. A is equals to X. X is the element of A and X is element of B. On the Venn diagram would be like this one, which is on the picture here.
Okay, just so to cut you there. If you are reading this set builder notation, it's just that X such that X is an element of A or X is an element of B. That's how you read that.
Okay, such that. All right, thank you, sir.
Yeah.
This is similar to the logical OR operator. Examples: union. The union of the sets 1, 3, 5, and 1, 2, 3 is the set 1, 2, 3, 5. That is 1, 3, 5 union 1, 2, 3 is equals to 1, 2, 3, 5. The group of students at your school majoring in either mathematics or computer science or both is the union of the set of all computer science major and mathematics major at your school. I don't know if can I explain? Yes, sir. Can I explain?
Yeah, if you want, yes, you can.
Okay, can you go back to the previous slide? I just want the Venn diagram. Okay, guys, when we look at that Venn diagram on the slide, there's A and B. Here it's saying that A has got its elements is 1, let's say 1, 2, 3. And there B, there's 1, 2, 3, 5. So the elements that are both in A and B is union between A and B. I don't know if there is a question over there. If there's no question, let's move on to the next slide. The next one.
Are you not on the set intersection?
No, it's showing me example of union.
Okay, let me just try to think. I've changed it from that one. Now I'm on set intersection. What about others?
On the set intersection.
Set intersection.
Okay,
Set
so
intersection. Set intersection.
okay, so let's see from Anthony
I
towards.
think my network is very down. It's my network cutting off and on. I can't see the set intersection on my side.
What about other group members? What about other group members? Maybe they can just, you can have someone who can come in and just finish the presentation.
Okay, for set intersection. A intersect B is a set of all elements that are in both A and B, denoted by A intersect B, that symbol. And then an element X belongs to the intersection of the sets A and B if only X belongs to A and X belongs to B. If the shaded region represents the intersection of A and B, the shaded region represents the intersection of A and B. This is similar to the logical AND. The two sets are called disjoint if the intersection is the empty set. For example, if A is 1, 3, 5, 7, and 9, and B is 2, 4, 6, 8, and 10, because A and B are not a set, A and B are disjoint. And then we have the set complement. A complement or not A is the set of four elements in the universal set, but not in A, denoted by the A with the dash on top. An element belongs to A complement only if X is not a subset of A. That is, A is is X being an element of U, and then X not being an element of A. The shaded area outside the circle representing A is the area representing A complement. Example 8, let A be A, E, I, O, U, where the universal set is the set of letters of the English alphabet. Then the complement of A is B, C, D, up to Z. The complement operator is similar to logical or not and is reflexive. That is, complement of A
It's
is equal
just
to
like
A.
it's just like the complement of a complement of A is equal to A. That's what they are saying. If you take the complement of a complement of A, you are going to get an A.
Thank you. So I think we move to the next slide. The set difference, or A minus B, is the set of elements that are in A with those that are in B subtracted out. Another way of putting this is the set of elements that are in A but not B is the A complement of B non-complement. Then the difference of set A and B is sometimes denoted by A and B. The element X belongs to the difference of A and B if only X is an element of A and X is an element of B. So, in other words, A minus B is equal to the subset X by X is an element of A And then inverse of X is an element of B.
Here on set difference, Tim, I think it's just as simple as what you are seeing on this Venn diagram. When you are saying A minus B, you are just saying we want those things which are only in A but not in B. So that's why you are seeing that A minus B is also identical or equal to A intersecting B complement. You just want those elements which are only in A but not in B as well as not in the universal set. So the set difference is just like that. X is such that X is an element of A and X is not an element of B. That's what we have here. Just like that. That's the set difference. We can continue.
We can go to the next slide. Symmetric difference. Given two sets, the symmetric difference is a set of elements that belong to either one or the other set, not both. Like if you can Venn diagram. The union of A and B minus the intersection of A and B is equal to this equation minus B union B minus A.
On symmetric difference, you are just looking for those elements which are in A and in B, but not in both. Just like that. Elements which are in A and in B, but not in both. So we are just excluding the intersection. That's the symmetric difference of sets. That's the symmetric difference of sets.
So we can move to the next slide. Example, let U let the union of set 1, 2, 3, 4, 5, 6, 7 A is equal to 1, 2, 3 sets and B has the elements 3, 4, 5, 6. So in the first example, the A intersect B, sorry, is 3. In the second, the union of A and B is 1, 2, 3, 4, 5, 6. And the third set is B minus A is 4, 5, 6. And number 4, A minus B, A minus B is 1. B complement is 1 and 2. So these are the elements in.
There is a hand by Grace. There is a hand by Grace. You can come in. Grace, are you going?
Sorry. A minus B. A minus B. I think it's 1 and 2, if I'm not mistaken.
Yes, I saw it as well. Because I am sure those elements which are in A but not in B is
Not
1
in
and
B.
2. Yeah, we are looking for elements which are in A and not in B. So there is a 1 and 2. Those elements are only in A but not in B. So A minus B, there was supposed to be a 2 there. So it's a 1, then 2. So here there's a need of correcting this one. It was supposed to be 1, then you put a comma and then you put a 2. Just like that. That's the correct answer there. Thank you, Grace.
All right.
You can continue. You can continue.
And for the last one, number 6.
The symmetric difference. Yes, you can continue.
Symmetric difference. It's 1, 2, 4, 5, and 6.
Why 1, 2, 4, 5, and 6? Why 1, 2, 4, 5, and 6? Unless you want to contribute, I think you can contribute because I'm only seeing your hand, only your hand. You can contribute, Grace.
The symmetric difference of asymmetric B, is it okay? Asymmetric B, we're looking for those elements that are not both in A and that are found in both A and B. Like you said, in simpler terms, we're just looking for the intersection.
No. On the symmetric difference, it's a symmetric difference. We need those elements. Yeah, it's symmetric difference. So we need those elements which are in A and in B, but not in both.
But not in both. So we're looking at the union of A
and B, but excluding the intersection.
The intersection part, yeah.
Yeah, exactly. So maybe if you look at A, you've got a 1 and a 2, which also is not in B. So if you look at B, we've got a 4 and 5 and 6, which are also not in A. That's why we've got 1, 2, 4, 5, 6 there. So I think that's all on sets, though there is a part on set identities which is not in here. I think as a class also have to go and have a look on it, on set identities. I'm sure it was supposed to be included here. So as a class, just go and look for that. I'm sure on your portal, those things are there. The formulas are there for set identities. So do we have questions for this group? Do you have questions or contribution for this group? Questions or contribution? Do you have questions or contribution? Colin, there's a hand by Colin. Do you want to say something?
No, say you have already explained it. I wanted to contribute on the symmetric differences.
All right, it's okay. What about others? What about others? So if there are no questions, I think we can call it a day. And then group two, please, just send me your group two, just send me your presentation. Just send me your presentation. Group two, just send me your presentation either today or tomorrow so that I can schedule your presentation.